Okay, good morning. Let's start. In the previous lecture, we were discussing about important things and the very important parameter of moisture, which we were discussing, that we named as adiabatic saturation temperature and wet bulb temperature. Okay, and if you recall, we found that at state A, when the moisture is not saturated, the pressure of water vapor is less in comparison to the vapor pressure, and it is the water vapor in the moisture is in the superheated state. Okay, and if we do cooling from point A, we can do two things, even three things. If I give you the entire picture, then say this is your point A. So first point was that from point A I have done cooling under the constant pressure conditions. So when I have done cooling under constant pressure conditions, I reached to this point D, which is my TD. And TD temperature is something which is called as the dew point temperature. Is this one clear? So in this case, what we have done, from point A, when we came to point D, temperature has decreased from TA to TD. So when temperature has decreased, the moisture handling capacity of the air has decreased. Whereas from process A to D, the moisture content within the air remained same. Okay, so mass of water vapor in the air has not changed, that remained same, but the moisture holding capacity decreased. That's how it reached the saturated state. Second thing, I said that if I add on, if I have water and if I adiabatically allow the water to evaporate, okay, then it means if adiabatically allowing water to evaporate, it means enthalpy of air itself, or energy of air itself, is used to evaporate water in order to provide the latent heat of vaporization. So I will be having process something like this, and with this process at the saturated state, whatever temperature I will be getting, that will be my wet bulb temperature. Okay, and how we can achieve this process A to B, that also I have explained with the help of this adiabatic saturation chamber. Is this one clear? Now, third thing is, let me keep the same temperature. I am not decreasing temperature, but what I am doing, at the same temperature I am adding some moisture. Okay, now if I add that moisture, and temperature of moisture I have to maintain at the same temperature condition, it means the water vapor temperature which I am adding to the air, that should also be equal to that of the temperature of the moisture TA. Is this one clear? Then only there will not be any enthalpy exchange between the two. So it means that enthalpy of the moisture will be equal to enthalpy of the water vapor which I am introducing. Okay, so water vapor, it means I have to introduce this water in the gaseous phase in such a way so that the temperature of that water vapor is equal to that of temperature of the moisture. So in this case, what will be happening, say if I added X amount of water vapor, of course temperature will remain same, but I will be coming closer to the saturated state. So say I have come to some point C. If I added slightly more water in the vapor state, then I will be coming to say this point. Likewise, I can come to saturated state like this also. Okay. This process is something from say A to E. This process is called as pure humidification process. So by the process of pure humidification also, I can achieve the saturation state. How to do pure humidification process in detail, its entire analysis I will be discussing subsequently. Okay, but these are some of the ways by which from any given thermodynamic superheated state of water vapor, I can come to the saturated state. Is this one clear? Now, whenever we were discussing about the adiabatic saturation temperature, we found one equation, and this I called as equation for adiabatic saturation chamber. In this equation we found that our requirement is to calculate T star, okay, and WS star, HFG star and HF star, all these are nothing but function of the T star itself. So it means that in order to know all these parameters for this equation, I first must know the value of T star, and ultimately from this equation I am trying to calculate T star only. So it means this is an implicit equation of T star. So how I can do these estimations? What I need to do? I need to basically assume the value of T star, then obtain these parameters, then with the assumed value I need to see if my equation is being satisfied or not. Then what is my residual? Based on the residual I need to keep on doing the iterations unless or until my equation is satisfied, and once equation is satisfied, that will be the corresponding value of wet bulb temperature. Is this point clear? Anyone is having any doubt about this? Okay, now let's come to one interesting fact. So the point is, whenever you will be doing engineering calculations, say you have to design a building, heating system or cooling system for a building, it is not possible for you because design will be changing at each and every stage. Say once you have this parameter, then later on you will be introducing something else, so you will be having so many iterations in the design itself. So at that time, if for just obtaining a single parameter, that is wet bulb temperature, if you have to do thousands of iterations, then it will be becoming a cumbersome process. Okay, so that's why typically what we do, we try to frame some property diagrams with the help of which we can directly refer to that property table or property diagram. Like for steam we go for the Mollier diagram. Have you heard of Mollier diagram? In Mollier diagram, a plot in between enthalpy and the entropy, specific enthalpy and specific entropy, is called as Mollier diagram, and that contains all the data like constant pressure lines, constant temperature lines, and of course abscissa and ordinate itself is entropy and the enthalpy. Okay. So likewise, from the single chart I can determine the properties at all the states: compressed state, superheated state or saturated states. Okay. So similarly here also we try to use one very important diagram which is called as the psychrometric chart. Okay. Of course, we will discuss about the psychrometric chart, but before that, one or two small things I would like to inform you. So whenever we will be doing experiments, okay, so it may also becomes important sometimes in experiments to measure the values of different parameters. For example, if you have moist air, okay, and I have to characterize in this room also I will be having moist air. So if I tell you that you have to determine relative humidity of this moist air, temperature of this moist air, and wet bulb temperature of moist air, dew point temperature, how you will be able to determine? Or what is the enthalpy content of moist air present in the room? So how can you determine? So first point is, thermodynamically we know that for representing the thermodynamic state of the moist air on property diagram, which just now I told psychrometric chart, I require how many independent properties? 3 independent properties. So it means for this room, first experimentally I must be able to calculate the 3 properties. If with the help of these 3 properties, then I can calculate all other parameters, because then I will be easily able to represent that state on my property diagram. So what could be the 3 important properties? First thing is, if I use barometer in the room, then I can calculate the pressure. So with barometer I will be able to calculate total pressure P. So first important property which I would be able to easily calculate, that is pressure. Second important property which I would be easily able to calculate, that is, if I just put a thermometer in the room, that thermometer will be giving me the temperature of the room. Okay. the temperature of the room which is measured by thermometer, that temperature is something which is called as dBT. What is the meaning of dBT? Dry bulb temperature. Okay, this temperature is called as dBT, dry bulb temperature. Now what do you think the third property which I can easily measure experimentally? If I have to measure dew point temperature, what I need to do? I need to put a cooling coil over here. Then I need to maintain cooling coil at different temperatures. Then I need to understand that at what temperature first dew formation is starting from the air. That's a complex process. It will be taking long time. Okay. Can you measure the amount of vapor content in this air? You cannot measure. That is also a challenging process. So third important property which we can easily measure, that is our WBT, wet bulb temperature. Now you tell me how we can measure wet bulb temperature. When we measured the temperature of the room using thermometer, then you can see when we have a mercury thermometer, okay, there is a thin tube and inside that tube we are having mercury, and at the bottom of that glass tube there is some metallic arrangement, okay. And typically if you go to doctor for your fever temperature measurement, so how they do, either they ask that tip to place below your tongue, or either they ask to just, you have to make contact with that top front portion. What is that top front portion called? So this is your thermometer, there is tube, inside the tube there is mercury, and then at the bottom there is this portion. What is this portion? This is called as bulb of the thermometer. Okay. So whenever the bulb of the thermometer is dry and you are measuring temperature, then it is called as dry bulb temperature. If I just put a wet wick on this, a wet cloth, porous wet cloth, just I have dipped in water that cloth and wrapped about the bulb of the thermometer, and then I allowed air to flow over the bulb, then what will happen? When that air will come in contact with the bulb, during the process of penetration through that wet wick, it will evaporate water, okay. So once it is evaporating water, its energy content will be decreasing, okay, and ultimately the air will try to reach to the saturated state. So if air is coming to saturated state, when it is making contact with the bulb of the thermometer, at that time whatever the temperature thermometer will be giving, that will be nothing but my wet bulb temperature. Okay, so we have maybe have you taken heat transfer lab, or you are taking in this semester? In this semester. So this we have one refrigeration and air conditioning test rig in the lab. So is that experiment being done? Any one of you have performed the experiment? So did you see their wet bulb temperature and measured it? No. Okay, so they have not shown you that measurement of wet bulb temperature. Okay, so maybe in our lab probably I think there is one set of thermometers, like there is one holder, in that holder there is one thermometer with no contact of wick, then there is another thermometer which is having some wet wick contacting the bulb, and that is having some handle. So because we are not allowing air to flow over that, so what we do with that handle, we just rotate it, okay. So once these rotates, it means air contact with the wet wick increases, and after rotating for some duration we check that what is the temperature, and whatever temperature we read from these two different thermometers. Okay, so one gives us the value of dBT and other gives us the value of WBT. Is this one clear? So this is the easiest method for measuring the wet bulb temperature. So other than pressure and dry bulb temperature, wet bulb temperature is an parameter which can be easily measured, and once these three parameters are known, then from the thermodynamics I can represent this thermodynamic state and I can determine all other properties such as dew point temperature, humidity and other things. Is this one clear? Now from this diagram also one interesting fact you have to see. In this diagram, what is the temperature of point A? Point A temperature, if I measure it, is unsaturated air temperature or unsaturated moisture temperature. So unsaturated moisture temperature will be equal to temperature of the moist air. So it means temperature of point A represents nothing but my dBT. Okay. When I will be doing this A to B process, so I told you that we will be bringing wet wick in contact with the air. So that process is taking place from A to B. So whatever the reading is given by the thermometer during rotation, that is my wet bulb temperature. Okay. And whenever I have done cooling of this air such that my dew formation starts, that is my dew point temperature. So from this diagram I can see that my dew point temperature is less in comparison to wet bulb temperature, which is less in comparison to dry bulb temperature. So typically this is the order of the temperatures, dew point, wet bulb and dry bulb for unsaturated air. If I have saturated air, what it means? Saturated air means it contains the maximum amount of moisture which it can hold. So if air is saturated, whether you measure temperature using dry bulb or wet bulb, both will be giving the same reading. And when you are having saturated air, as you started cooling, immediately dew formation will also start. Okay, so for saturated air, T dew point will be equal to WBT will be equal to dBT. Okay, is this point clear? Now let's start with the property diagram, because of course we have even more thermodynamic relations and charts, okay, thermodynamic relations and tables with the help of which we can determine all the properties. But again, using relations will then make the process complex. Okay, so to avoid that complexity, we will be actually using a common chart on which we simply need to represent the thermodynamic state and we can determine all other properties. Is this one clear? But before that, if you have to say, in case use the relations and relations are not given, then if you need to calculate partial pressure of the water vapor, then for calculating partial pressure of water vapor, there are some equations, empirical equations given. So these are famous equations. Let me write these equations here. Modified PW can be written as PWS star minus 1.8 into P T minus T star divided by 2700. Can you tell me what is PWS star? Corresponding to wet bulb temperature, whatever is the Saturation pressure. So saturation pressure of water, but corresponding to which temperature? Corresponding to wet bulb temperature. And P is total pressure, T is dry bulb temperature. This T, let me use capital T for the temperature. So capital T is dry bulb temperature and capital T star is wet bulb temperature. Second equation is modified Farrell equation. This is PW equal to PWS star minus 1.8 P minus PWS star T minus T star and third equation is sorry, make this correction. So this I have written the carrier equation. Now let me write modified. Okay. Is this one clear? So these are just empirical equations. Maybe sometimes it may so happen that if property tables are not provided for steam table, okay, because some data, okay, but steam table also is required. But if say DBT and WBT are given and you need to calculate the partial pressure. So why partial pressure? Because if you have saturated air, then vapor pressure you can easily calculate from the steam table, okay. But if you have unsaturated air, then it will be difficult because it will not be at the saturated state. So then you may need some equation which can give you some idea about the partial pressure for unsaturated air. Is this one clear? Now let's talk about the psychrometric charts. So of course, these charts have evolved long back. So initially Goff and Gretsch has provided some tables for representing the thermodynamic properties of moist air. So these tables in graphical form are represented, and these are called as the psychrometric charts. Okay. So some of the initial plots included dry bulb temperature as abscissa and specific humidity as ordinate, okay, to represent the psychrometric chart. In between, then Mollier came, and Mollier, what he did actually, he represented psychrometric chart by using enthalpy and specific humidity. So one of the axes was enthalpy and other axis was specific humidity. But later on, the next people who have presented these charts and tried to determine the properties of moist air, they all presented the tables in the form of DBT and specific humidity. So at present, as per the American Society of Refrigeration and Air Conditioning, whatever charts they are providing, they are also using DBT along abscissa and specific humidity along ordinate. Okay. So majorly this is one of the standard form which is being considered nowadays for standardization of the psychrometric chart. Now, whenever I am talking about the psychrometric chart, you can see that I have only talked about two coordinates. One is DBT and other one is specific humidity. But we know that whenever we have to represent the thermodynamic state of moist air, we must know how many coordinates? Three coordinates. Okay, for moist air, three are needed. Two will be only, we will be able to only do when we are having the saturated moist air. But if unsaturated moist air is, then three are needed. What is the third parameter? Third parameter is basically pressure. Okay. So as moist air for most of the air conditioning applications is having pressure close to the ambient pressure. Okay. And other important point is you have different air conditioning equipment. For example, in this duct, air is coming from somewhere, then one portion of the duct is sucking air from the room. So you will be finding that flow is always governed by the pressure difference. So it may come to your mind that the pressure from one location to other location, whenever the fluid is moving, pressure will be changing. Is this point clear? But we have to understand this point very, very carefully, that whenever we move the air across various air conditioning equipment, first thing is we design the ducts in such a way so that pressure loss is minimum. And second important fact is the viscosity of moist air is very, very less. So being the very less viscosity of moist air, ultimately what happens, the amount of pressure drop from one component to one location within the component to other location is actually very, very less. So if delta P is very less, in that scenario I can assume that at various locations the pressure is same, and that pressure is nothing but equal to the ambient pressure. Is this point clear? So that is the reason the psychrometric chart, whatever standard psychrometric chart you will be finding for moist air, only one chart is available. Of course, if you have to, in certain specific, very specialized application, if pressure has to be increased or decreased, then you have to construct the property diagram for that particular pressure. But for standard air conditioning applications, whenever you will be referring to any of the text, only single psychrometric chart is given, and that chart is corresponding to ambient pressure. Is this point clear? So one property is nothing but my ambient pressure, and reason for this is in standard applications pressure drop is negligible. Okay. Now, if you refer to psychrometric chart, maybe knowingly or unknowingly, whatever I am going to draw now, knowingly or unknowingly, in many textbooks of your engineering thermodynamics or other things, you might have seen this shape. If some of you have seen, let me know. Any one of you have seen chart something like this? No? So this side what I am having? Temperature. Okay. And mostly this in vertical scale, this temperature is nothing but my dBT. Is this one clear? Then what else I am having? In this side I am having specific humidity. Unit of this temperature is typically degree Celsius in most of the charts, and specific humidity will be kilogram of water upon kilogram of dry air. And in many cases you may find that for water vapor, because mass is very small, okay, so the unit can be gram of water by kilogram of air, or if it is kilogram of water by kilogram of air, then you will be finding along with this 10 to power 3 is also written. It means that whatever is the value marked over here, that value has to be multiplied with 10 to power minus 3. Okay, is this point clear? All are agreeing to this point? Now, on this plot, I have one line something like this, and this line is considered as phi equal to 100%. What it means? This line is representing all the states having relative humidity 100%. Okay, and it means this line is nothing but my saturation curve for moist air. It is saturation curve. Okay. Now how I can represent the saturation curve? It's very simple. This is one of the simplest line to represent on this. Okay. So I know my W is what? (0.622) into PW upon P minus PW. But I also know that if I need to calculate for saturated air, then PW will be becoming PWS. For saturated air, PW will be becoming PWS. All are agreeing to this point? And what I simply need to do, I can select different temperature values. At each temperature value, I can go to saturated steam table. From the saturated steam table, I will be measuring the corresponding saturation pressure. That will be becoming my PWS. I will be substituting in this formula, and for all the temperatures, I will be getting the corresponding values of W. All of you agree to this point? From this simple formula, I can obtain this entire line. It's very easy because simply I need to go for PWS. Okay. However, you have to also represent one. You have to also consider one point, that if you have to represent this table with 100% accuracy, then I must multiply a factor F over here. What is F? Correction factor, which is a function of temperature. So when I have known temperature, then for known temperature from Goff and Grach tables, I can calculate the value of F as function of temperature. I can calculate the value of PWS from the saturation steam table, and after substituting here temperature, and I will be getting the value of W. So for all T I am getting all W, and this equation is valid only for saturated state because I am using PWS over here. So it means all these data points, when I will be joining whatever the line I will be getting, that will be my saturation curve. Anyone is having any doubt about this? Now, of course, I will not explain the construction of all the lines, how these are constructed, but maybe some of the lines I will try to explain some characteristic features. Now, on this curve, I have this type of multiple lines. And all these multiple lines, what these are representing? Different values of phi. For example, this can be 90%, 80% or 50% relative. Is this point clear? Then other important aspect comes WBT. Because just now we understood that experimentally I cannot measure specific humidity. I cannot measure relative humidity easily. Of course, I can measure with some complicated equipment, but easily I cannot measure. The parameter which easily I can measure is WBT. Okay. So I must also know that how WBT can be represented on this diagram. Because if I know dBT, I know WBT, pressure I know, then I can easily represent the state and calculate all other parameters. So let's see the variation of WBT. For WBT, one important thing already we know from adiabatic saturation chamber, we have calculated the equation of wet bulb temperature. Okay, what was the equation of wet bulb temperature? Just now I shown you that implicit equation, Ws star minus W into HFG star equal to 1.005 plus 1.88 W into T minus T star, means some other variant of the previous equation. Okay. Now, if I do dt by dW at constant T star, you got my point, what I am doing? I am taking the derivative of this temperature with humidity, and this I am taking at which value? Constant value of T star, constant value of wet bulb temperature. If I do this, I will be finding it to be minus HFG star minus 1.88 into T minus T star divided by 1.005 plus 1.88 W. Sorry, it will be plus only. This will not be minus. Okay, what is this value? Humid specific heat. Humid specific heat. So humid specific heat, typically for calculating humid specific heat at standard temperature and pressure conditions, humidity is considered, relative humidity is considered 50%. Okay. So by using 50% relative humidity, if I calculate this number, I will be getting it to be 1.0216. Okay. So 1 divided by 1.0216 HFG star plus 1.88 into T minus T star. Now you understand this equation. Whatever is the characteristic of this equation, same will be characteristic of this constant wet bulb temperature line. Is this one clear? Now if you see in this equation, what is first dt by dw? Dt by dw is nothing but slope, because this is my basically 1 by slope along this side. Okay, this is w, this is t, so it is slope along the ordinate axis. So slope of ordinate axis is coming out to be 1.01 divided by 1.0216, which is a constant value, into HFG star. What is the meaning of HFG star? Value of latent heat of vaporization at T star. T star is fixed, so HFG star will also be fixed. Plus 1.88 into T minus T star. Here again T star is fixed, only variable over here is T. So it means that whatever this slope I am having for constant wet bulb temperature line, it is not entirely a constant value, because at different temperatures this will be having different values. But one important point is HFG star is very large in comparison to 1.88 into T minus T star. Okay. So if HFG star is very large in comparison to this value, what it means, I can remove this value and I can simply say that my slope for constant wet bulb temperature line is nothing but equal to simply HFG star by 1.021. Now it has become a constant slope. Is this point clear? What it means? It means that my constant wet bulb temperature lines can be represented as straight lines. Of course, in actual practice, at each and every point, slope will be different, because when I am moving like this, then at every point every point temperature is changing. That will change T minus T star value. Okay, but the value is very small, so change is very small. So I can approximate WBT line in the form of a straight line. Anyone is having any doubt about this? So all these black colored lines are nothing but my constant WBT lines. Is this point clear, or anyone is having any doubt? Okay. After constant WBT lines, let's go to enthalpy lines. I know that enthalpy is HS star saturated enthalpy minus WS star minus W into HF star. Okay. What is HS star? Saturation enthalpy at T star, which is wet bulb temperature. So if I have and what is HF? Saturated liquid enthalpy. This is saturated vapor enthalpy. This is saturated liquid enthalpy at T star, and WS star is specific humidity at T star. Saturated humidity at T star. All are clear with this point? So for a fixed value of T star, this parameter, and this parameter, all these three will be a unique value. Is this point clear or not? For a constant value of T star, what is the meaning of constant value of T star? This value. Along this line, my T star is constant. So along this line, you see this parameter, and this. These are fixed. But which parameter is changing? W. So if you move along this line, your value of W is actually decreasing. Is this point clear? So as your value of W is decreasing, this difference of WS star minus W. What is WS star? WS star will be this value. For this line, this will be WS star. Okay. Now WS star, as you move along the line, your W value is decreasing. So overall, your WS star minus WS is increasing. It is increasing. And it is HS star minus this. HS star minus of this. What it means? It means HS star minus of some delta H, which will be coming from this value. So it means that from this point, whenever you will be moving in downward direction, your enthalpy, if you start from this point, then your enthalpy value must go little down. Is this point clear or not? If you are starting considering this point to be HS star, then your enthalpy value will keep on decreasing. All are clear with this point? Please tell me. This is important to understand, okay? And please also note that. And if you start from this point, then what will be happening? If you start, assume that an enthalpy line is starting from this point, then your enthalpy must increase in the above direction, because here enthalpy will be less. That was the situation. This is HS star, and when you have come to this point, then your actual enthalpy H is less than HS star. Okay, so it means you are going. So if you start from this point, then enthalpy must increase, so it should be like this. So that's why the slope of constant enthalpy line and constant temperature line, constant WBT line and constant enthalpy line is something which is a relative parameter. It means the point at which you are equating WBT and enthalpy, from that point it will be deciding whether slope will increase or decrease. Let me remove this for the time being. So all these lines are nothing but what are the blue colored lines? These are constant enthalpy lines. Okay. So usually on psychrometric chart, you will be finding some inclined scale over here. And that inclined scale represents enthalpy in kilojoule per kg A. It means kilojoule per kg of the dry air. And if you extend these lines on this scale, you can read the value of corresponding enthalpy. Is this one clear? So from here you can directly read the enthalpy value from your psychrometric chart. So this is your job today, that all of you open your any textbook or just Google psychrometric chart. You will be able to see all these lines. Get familiar with the psychrometric chart, how values are given, what are the scales, etc. Other than this, whenever we deal with the air, for air conditioning equipment, there is one very important condition. The important condition is, for example, for solids, generally what we say, how much is the mass? 5 kgs, 6 kgs, okay. Whenever we deal with the liquids, when you go to purchase mustard oil for your home, or when you go to petrol pump, then you ask liters, 1 liter, okay, say 30 liters petrol you will be filling in your car. Whenever comes the air, then typically, of course, for water also there can be continuity. For example, when water is coming in your tanks, then water is continuously flowing. Whenever you select the pump, typically for pump it is specified liters per minute. Okay, that is the capacity of the pump. In the similar way, whenever you will be designing the air conditioning system, or basically in air conditioning system, what you need to do? You need to take the air from the room, process it, and then again supply. Okay. So air conditioning equipments are generally specified in terms of the volume flow rate of the air. Okay. So common unit for specifying the air conditioning equipment is either meter cube per minute, or it is also known as cubic meters per minute. So that is the unit. So if you go to market and ask that you need a blower, okay, for circulating air, they will be telling you simply how many cubic meters per minute you want to flow. So if we have to deal with the volumetric flow rate, I must know the density of the moist air. Because if I don't know the density of moist air, then I will not be able to calculate this. Okay. And density of moist air, because moist air, water vapor present in the moist air can be easily represented with the ideal gas behavior. So from the ideal gas equation, I can easily calculate the value of density of the moist air. Okay. So using the ideal gas behavior, you will be finding that on your psychrometric chart, there will be one additional line, and that additional line is something like this. With very steep slope. And what are all these lines? These are constant specific volume lines. So this is the specific volume of the moist air. So it means that after representing the thermodynamic state on this particular chart by using three parameters experimentally which are easy to measure. One is dry bulb temperature, you can locate from this, pressure is already there. Other is wet bulb temperature. You can calculate enthalpy, you can calculate specific volume, you can calculate specific humidity. Okay, so all other related parameters which are required for analysis can be easily calculated. Is this point clear or not? Clear? Then other than this, there is one more parameter which generally is present on the psychrometric chart. Along with this scale of specific humidity, there is one more scale behind the specific humidity. There is one more scale over here. Okay, and this is SHF. SHF is known as sensible heat factor. Okay, so on a psychrometric chart, along the ordinate, one more secondary axis is there, which is the scale of sensible heat factor. Its value typically ranges from 0 to 1. Okay, its value typically ranges from 0 to 1. What is sensible heat factor? We will be discussing in the next lecture with the help of a process. But before that, you have to understand that this sensible heat factor is nothing but the function of delta W by delta T. Where delta W by delta T, what is it? It is nothing but slope. Delta W, Y divided by delta T is delta X. So it is nothing but slope. So sensible heat factor is a function of slope. For using the sensible heat factor scale, one important point is marked on the psychrometric chart, which is called as alignment circle. So somewhere over here you will be having a circle like this. So please carefully observe your psychrometric chart. You will be finding a circle marked on the psychrometric chart. That circle is something which is called as alignment circle. And typically alignment circle on most of the charts, it is specified at 25 degrees Celsius dBT and relative humidity of 50%. In some tables it may be at 26.7 degrees Celsius and relative humidity of 50 degrees Celsius. Okay, and this alignment circle is always used in conjunction with the sensible heat factor scale for representing the process of heating and humidification and cooling and dehumidification. How this is done, that I will be explaining you in the subsequent discussion. Is this one clear? So all are getting familiarized with the psychrometric chart. This will be an important tool, because after this, whatever the problems we will be doing on air conditioning, everywhere we will try to use the psychrometric chart. Because if you use the thermodynamic relations, this will be taking too much of time. Okay, So here easily by just locating the state we can calculate all the properties from the single chart. So for engineering applications this is a very good tool actually. So that's why it is very popular as well for solving air conditioning problems. Is this one clear? Okay, so we will stop at this point and we'll discuss further in the next class.